So this is our final unit. I call it geology. Basically, we're going to talk about the history of Earth to the best of scientists' understanding of it. We're going to talk about rocks and how rocks allow us to know about time. And so we're really going to focus on a lot of things like fossils, archaeology, geology. That's a lot of the stuff we're going to talk about. And one of the first things I want to begin with, though, is that this is one of the, how do I describe this? This is a science for sure because we use scientific techniques, but it's a science that's maybe a little bit less concrete than physics. For example, in physics, I want to know how this pen is going to move. And so I throw it and I test it and I make a prediction and I can actually confirm that prediction. If I want to make a hypothesis like I believe that the Earth is X number of years old, we really can't test that because we can't actually go back in time. Does that make sense? And so, not that this is not science, but I think it's very important to be said right when we start here is that science is always developing. And if we ever find new and better techniques for trying to figure things out, sometimes we change our science over time. So I'm going to say, not that I don't believe this, because there's definitely some different opinions as to how our Earth was formed and created, or however that works there. But this is what scientific evidence suggests. That's how I'm going to phrase this. And to the best of what we know about it, this is what we can tell. Does that make sense? Okay. So that's why I'm going to begin with my first slide here. I actually pulled this directly out of our textbook. It says that scientists generally agree the Earth is about 4.5 billion years old. Okay. Now I've got some proof and some evidence for this. Okay. But I mean, I should start by saying that not all scientists necessarily believe this. It is still challenging because how do we know for sure? Right. Basically, you know what they do is they kind of make the assumption that okay, time has been going along like this, and so then they try to rewind time and say if we could go backwards, here's where things would have come from. And that's where the physics idea of the Big Bang Theory actually comes from, is that if we could literally rewind the universe, they believe it literally started from a singularity that exploded. Problem though, we can't actually go there and confirm this. And so evidence suggests this is the truth, but maybe 300 years from now, when we know more about gravitational waves, we'll change our theories. Okay? And I think that should be said for all sciences. The last thing we're going to talk about in this unit is actually climate change. And I think that really applies to that section too, is that when we learn more about how our climate change really works, we have to adapt our theories and our predictions or suggestions. And so, unlike in chemistry, where when you know how I made the clock work, I made a prediction that I could make the clock work, and then I actually made it work because I can actually test it. You know what I'm saying here? This stuff really hard to test concretely. So, the definition I need you guys to know though is this one here called deep time. Okay, basically the idea is that Earth has had a long history of development. That's the belief, is that the rocks and the fossils on Earth is evidence that Earth has been around for millions and millions of years. I am not an expert on this by any means. Okay, but maybe you guys have heard of some of these things before. This would be like the Jurassic era. Jurassic era is one that people have heard of, basically because of Jurassic Park. Right? What happened during this area? Yeah, that's where we believe the dinosaurs were from. And as we kind of go either closer to our current era or to the further away eras, they're kind of given like different naming schemes. I will not make you memorize this, okay? Because I don't know what order they come in. I'm pretty sure like a paleontologist, like you guys know what that would be, a paleontologist, someone who studies fossils. They probably would have all of these things memorized for sure. But I mean, we'll just write them down as we go along. So, anyways, deep time is the idea of time really existing for a long period of time. So if you want the definition of geology, then, which I call this unit, it's where we study Earth's structure. Basically, like what is Earth made of? And there's another problem with that as well. We believe, and I'm going to say this a lot here, we believe we know what Earth is made of, but we don't know for sure. Because can we go to the inside depths of the Earth? No. Now we can run tests, and I'll show you some of the tests that we do run and what we think occurs. And I mean, I don't disagree. I think there probably is a core to the Earth. And I think there probably is like molten magma inside, if you've heard of that stuff before. But like, can I actually physically go there and check? Well, no, I can't. So, so we're going to talk about what Earth is made of, and then we're also going to talk about, to the best of our knowledge, what history it has and how it's changed over time. And a lot of it really does belong to things like fossils. And so old rock formations like this one right here is kind of the clues that we have. Okay. Paleontology then is kind of the field I just mentioned there, where if you're someone who studies rocks and fossils, you're an archaeologist. You guys ever watched Friends on Netflix? Ross on Friends would be a paleontologist, right? When Joey had to fill out the hospital form for what he does, he wrote down dinosaurs. You guys ever see that episode? Job description. He does dinosaurs. Yeah. Oh yeah, I can get you one. Yeah. There you go. Okay, so this then leads to the question, well, okay, sure, we find fossils in the ground, and we think they belong to prehistoric creatures. Fair enough. How do we know how old they are? That's really a challenge as to, well, how do we know that this is 10 million years old? How do we know that this is 40 billion years old, right? And so that's really what we're going to talk about today is my initial topic here is how scientists try to measure time knowing that we really can't go back in time. Recorded human history is really only about 5, 6,000 years. And so we really can't go far further beyond that in terms of what humans have been around for. And even that being said, um, human like most human history has really only occurred in about the last say 100 years. In terms of like books that are still around, right? Are there some books that are 200 years old, 300 years old, 1,000 years old? Yeah, I mean there's definitely ancient manuscripts, but like most of our recorded history, I mean, even more so, is really just with the advent of the internet, right? And so to know for sure what happened, yeah, it's challenging. Okay. So here's one of the first things that geologists look at to try to figure out how old the Earth is. The word is called an outcrop. Outcrop. And I found this picture in your textbook, which I think works really well. Basically, the idea of an outcrop is that land is not just flat. Okay, around here it's kind of boring because for the most part land is actually pretty flat. But if you have some really cool cliffs, or if you have like a river that is cut down to the bottom of a section there, you can actually literally see rocks from the top to the bottom. Okay? The single greatest example of this I know of is the Grand Canyon. You guys know the Grand Canyon down in like the United States there? Because literally you can go from the top down to the bottom and you can see all these layers, one on top of the other. And that's kind of the idea. So the definition of an outcrop here is a rock formation that appear above the surface of surrounding land. With the idea being that you can literally see like this little, desert structure right here. I know it's blurry, right? But you can actually see like different layers as you go up, right? A mountain would be an example of an outcrop, right? Like this could be a picture taken at what's it called? What's the provincial park just down the road there? Waterton, right? Like this could literally be a picture of Waterton, right? And you're literally seeing like, okay, look, there's some rocks that are sitting right here, and there's mountain ridges that we can see going up, right? These are like cliffs that could be off the coast of, I don't know, Ireland or maybe even Nova Scotia, right? And you can see the layers there, right? So anything like that is an outcrop. The idea being, like I've got on this picture here, that hopefully we can see how Earth was formed. Okay? In theory, this is kind of like your laundry basket. And again, this is the theory because we have no evidence to suggest otherwise. But imagine that you were digging through your laundry basket. Where would the oldest clothes be? The bottom. That seems the most likely, right? But again, that's kind of conjecture. I don't know that absolutely for sure. Hey. Yeah. Okay. Go hunt on some kids. Okay. Sure. Sure. Okay, so yeah, you guys hopefully kind of get the idea of the laundry basket, right? Is that I assume that the stuff at the bottom of the laundry basket is the oldest, right? And that seems like a fair assumption, but was was I necessarily there when the bottom layer got put there? Well, no, maybe Melissa threw those clothes at the bottom of the laundry basket, and then Kinsey threw the next ones in, and maybe without me knowing it, my daughter Cameron went through and rummaged through the laundry basket and mixed it up a little bit, right? And that's one of the challenges is that certain things can disturb the earth. Like for example, earthquakes, tsunamis, right? And that maybe messes things up a little bit, but we kind of have that assumption. The term I need you guys to know is called relative dating. This is not the same as when you have to take your sister to the prom. Yeah, I got a laugh out of that one. So relative dating basically means that as you look at the Grand Canyon here, The assumption, and it seems logical, we have no reason to think otherwise, but the assumption is that the lowest stuff down at the bottom of the Grand Canyon is probably the oldest, and then the stuff that's above it is younger and younger and younger. In theory, then, the topmost level should be the thing you put on last. Right? And that makes sense, right? Like, even just look at Emery's textbook and her phone there, right? I assume that her textbook went down before the phone. That seems logical. Do I know that for sure, though? Well, I don't know that I know it for sure, but it sure makes sense, right? That she probably put the textbook down first. Even this thing right here. I'm fairly certain that the water bottle fell over on top of the paper, right? But is there another explanation? I don't know. That's the whole point of science, right? That literally is the whole job of science, is to try to come up with the answer to that. So I found a picture here that I think kind of helps show the idea here. Over time, in theory, what should happen is new layers of rock should settle on top of each other. And so, like, even as like an ocean kind of carries sediments with it, what you should hopefully find is that the younger, we call it a strata. I'm not sure that I have that written down later, so why don't I write that word down here now? It's called a strata. Strata. Okay. A strata is basically another word for like a layer. And as each new layer gets deposited, we assume that this one down here is the oldest, and this one up here is the youngest. That's supposed to say youngest. Let's do it again there. Youngest. But again, what if there's an earthquake? How does that change things? Right? Might that disturb things a little bit? I've actually got a few more exceptions I'm going to show you in this lesson here, but for the most part, that makes sense. There's a law then. It's called the law of superposition. Superposition, which basically means that like what I've just said here, this layer up here would be the youngest, and then this one would be a little bit older, and this one would be a little bit older, and the further down you go, it gets older. And so the word we use then is stratigraphic sequence. And I'm going to go back a slide here and show you the Grand Canyon. You guys can literally see how there's like that little white line right about there that goes across there? See how there's like some lines that are kind of going along those? Like each of those then would be a new stratigraphic sequence where there's layers built on top of each other. And that's the cool thing about those outcrops is we can see that. Okay. So in terms of terminology, the law of superposition basically says youngest on top, oldest on bottom, and stratigraphic sequence is each of the layers. However, right off the bat, I already have an exception. We already know that there is a little bit of a problem with this, and it actually has to do with volcanoes and magma. So I'll let you guys write this stuff down first, and then I'll talk about the volcano magma thing in a bit here. Where's my water bottle? There it is. Okay, so law of superposition basically means that Earth can be dated relative to each other. Okay. Oldest stuff on the top, no, oldest stuff on the bottom, youngest stuff on top. Each layer is a stratigraphic sequence. But let me kind of try to draw you a picture of magma invading a rock here. So imagine you've got these layers. Here's a layer of rock. Here's another 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 layer of rock. One of the things that we believe about the inside of the Earth, and again, we can't really go there, but evidence suggests, is that some of these layers are like literally like liquids, and it's magma. You guys know what I mean by that? Like that's like I don't know, like think of any movie where they're like hovering over a volcano, right? And it's like Mordor, and they've got they got to throw the ring inside, and it's all this red liquid lava. You know what I mean? That lava would be a good example to use, right? Well, in theory, that liquid lava, because it's liquid, maybe it can find a way to like squish itself kind of up through the rocks a little bit. And we have a name for that. We call it an intrusion, where maybe it can actually manage to seep through some of the rocks on the way upwards. But here's the problem. The liquid magma was actually the oldest because it was at the bottom, but it managed to actually seep through. And we actually notice this when you eventually have, say, a volcano. So I suck at drawing. So imagine this is a volcano, and imagine the liquid magma from the bottom of the volcano erupts over the edges. And all of a sudden now, the lava is up here. Was it supposed to be up there? Well, no, because it was supposed to be down here. Does that make sense? So we already know of one exception to this rule right off the bat. So in theory, though, that does make sense, though, right? Oldest stuff at the bottom, youngest stuff at the top. I think I have a picture of an intrusion later in these notes, but basically the idea is, yeah, that somehow something manages to force its way up like this. That really, it was supposed to be down here at the bottom, but it managed to find its way up more. Do I have that picture? I thought I had a picture of the intrusion. Oh, you know what? I know where it is. It's in your assignment. Do you guys have your assignment nearby? That's where it is. I don't have it on the screen, so you guys will just have to find it if you have one. There it is. Does everybody have a copy of the assignment? Okay, can you guys find that picture after number 3 there? It basically has a picture of all the rock layers. And we may as well even do this question while we're speaking about it. Question 1 is about the law of superposition. We can kind of ignore that one for right now. Go down to number 3. It says this was a geographic profile painting by a guy named James Hutton. Question A, which layer would be the youngest layer of all those letters there? A, B, C, D, E, F. F, because I think D is pointing to the layer right below F. There's an arrow there. So yeah, I believe F is the youngest layer. What is E, though? E is called an intrusion, because can you kind of see how E managed to like force its way up there a little bit? All the rest of this has like some nice lines. They have perfect strata there, right? I know they're going a little bit diagonally, and I'll talk about a reason for that later. But somehow E managed to cut its way through. E could possibly be molten lava that's found a way to like bubble itself most of the way to the surface. Does that make sense? So that picture in there, that would be a good picture of an intrusion. Okay, anyways, moving on here. So here's what that means then. If we're correct and we believe that the youngest stuff's at the top and the oldest stuff's at the bottom, what we can do then is we can start to layer these things into what we call the eras and the periods. And where'd that one go here? For example, one of the eras is known as like the Precambrian era. And since it is the oldest, it's at the bottom. And as you work your way up, you get younger and younger. I had a picture, where was it? Right here, the very, very first slide. And that's kind of the basic concept, is that we currently live in what we call the Holocene period, because it's the highest up one. Right? But as you go further down, this is getting older and older and older. Okay? And so we kind of label those. I think there's even a chart in your, you guys know your data booklets with like the physics sheets? I think there's actually one of these in here that talks about all the different eras. And they go all the way from the Precambrian era, which is the oldest one, all the way up to the Cenozoic era. And so yeah, Precambrium's all the way down. Cenozoic would be up here. I got another definition I need for you guys to know. It's called an index fossil. Okay? And really, fossils are the key to figuring this out. Once they kind of have the idea of different layers going on here, those different stratas, when they find fossils inside the layers, the cool thing is that they then should have the same relative age. Okay? For example, let's say that I managed to find in the bottom of my laundry hamper my one blue sock. And I can't find the other blue sock. But I eventually managed to find it at the bottom of a second laundry hamper as well. Would it not be fair to assume that if I wore both those blue socks on the same day, that they're the same age roughly? And so if I found one over here and I find one over here, should they not basically be from the same time frame? So the idea being, say you find this really cool fossil over here in Africa. And let's say you find this really cool fossil over here in Europe. And they're like exactly the same. The assumption then is that, well, this one over here and this one over here, they must have been from the same time period, right? Because they're from the same time frame. And that's what this picture here kind of shows. So imagine that you had 4 different locations here. And let's say that you found this really unique fossil right here, this guy like that. Well, let's say I find that one also sitting over here. The assumption then would be that if this is from, say, the Cenozoic era, then, well, this one here is probably also from the Cenozoic era. Right? And so anything that you find in more than one location is called an index fossil. These guys right here would be a great example of index fossils. Because see how we find them all the time? And they're always at the bottom? And that would seem to indicate that they're probably the oldest, right? This would be the youngest, and that would probably be the oldest. And so then we can start to put together layers and say, well, this must have been the top layer. We call that one the Cenozoic era. Cenozoic era. Whereas this one's the oldest. This one maybe is from the Precambrian era. So if I go back a slide here, does that make sense? Index fossils that are found in different locations, but we think they have the same age. Now, here's the problem though. This is why it was called relative dating. We don't actually know exactly how old they are. We just know how old they are relative to each other. Does that make sense? Like, you ever hear some of those like silly riddles where it's like Alice is older than Bill, but Bill is older than Dwayne, and Dwayne is younger than Phyllis, right? I don't actually know that Alex is 19 and Bill is 12. I just know in what order the kids go. You know what I mean? That's the same problem we have right here, is that if this logic is correct, this then must be the youngest, but how young is this? Is this 25 years old? Or is it 25,000 years old? Or is it 25 million years old, right? Like, sure, we might believe this is the youngest, but how young? And so that's always been a problem that has plagued archaeologists because they really had no way of knowing for sure. Yeah. I'm going to come back to solving that problem later, but does that make sense, though, the idea of being able to pinpoint exactly how old? We just have relatively how old. So these next slides then really talk about the evidence we have, and it's all about fossils. Okay? A fossil, I've got this basically defined for you right here. A fossil is evidence of life preserved. There's actually a lot of different types of fossils, but if you have something that looks like it was alive and somehow it's been left behind, that's a fossil. I think when I think of fossils, the first thing I think of is dinosaur bones. That's probably what most people kind of think of right off the bat is, hey, look, here's some bones left over from a Tyrannosaurus Rex. Right? Well, that would be evidence of what once was life, hopefully. So, I also pulled this out of your textbook as well. There is a lot of debate about not only when, but how life began. Mike was actually, remember the PS2 guy? He was doing biology with the grade 10s over there. And he actually had them pose the question when they did the biology of, well, we've been talking about how cells exist, but like there really is no answer, no definitive answer. There's lots of theories, but there really is no answer in the scientific community that kind of says, well, where did the first cell come from? There's lots of belief as to what happened once the first cell decided to multiply and go together, and lots of evolutionary concepts, but really the idea of, well, how did we go from having no cells to having one cell? That really is still a challenging problem because we weren't there. Right? And here's the even bigger problem. Unlike most other sciences, like in physics, I can throw something and try to replicate the experiment over and over and over again. No one has been able to literally create life out of nothing, unless you're talking like Frankenstein movies, right? Like no one has been able to like put some stuff together and be like, and life start growing, right? Like life usually comes from life. You want to make a tree, you start with a seed, but you know where the seed came from? It came from another living tree. You want to make a new human or a new animal? Well, that comes from previous animals having, well, reproducing. Let's use that word, right? Does that make sense? Right? So life, as far as we've been able to ever reproduce, literally comes from other life. So then where's the question? Well, where did the first cell come from? So we really don't have answers to that question. But what we can do is we can look back at fossils and try to reconstruct what we think it looked like. But again, we don't have a time machine. So one of the words I need you guys to know, and I highly recommend that both these words that are bolded right here, that you put a note next to, because they are on one of your tests. So I was just looking them over earlier today, trying to think of what things I should suggest to you to study. The terms are stromatolites and cyanobacteria. Okay. So we really don't know where the cyanobacteria came from, but the belief is that cyanobacteria is some of the first cells that ever really existed. And the evidence that's left behind is that the dead cyanobacteria made fossils. Okay? Basically, the concept is that these bacteria, they left behind calcium carbonate when they died. So the bacteria lives, the bacteria dies, and it decays and it turns into calcium carbonate. I don't know if you guys know what calcium carbonate, but it's essentially like chalk. It's a chalky-like material. And as bacteria, you might want to watch my hands here, as a bacteria dies, and another bacteria dies, and another bacteria dies, and another bacteria dies, they build up on top of each other, right? And it eventually makes a fossil. And this actually original picture I had back here, that was actually a picture of stromatolite, which actually just kind of looks like rocks, honestly, right? But that's the belief, is that this right here, this particular rock formation, is actually a whole bunch of dead bacteria that literally built up on top of each other. So those are the two words I need you guys to know. Cyanobacteria, some of the initial basic cells, however they came here, died and formed fossils called stromatolites. So, however it is that life formed, not really needing to enter into that debate right now, but life formed, we have cells, I guess, right? Those initial cells, some of them, we call them cyanobacteria. And as they died, they turned into calcium carbonate, and that calcium carbonate hardened together into like a rock formation. And the fossil name we give it is called the stromatolite. If you want the picture, you okay? I'll talk to you about it more later, but this right here, this rock right here, is the picture of the stromatolite. So, remind me later. I'll talk with you when you come back. So, here's a slide that I found on the internet that kind of talks about different types of fossils. And I actually do have some of this on your quiz as well, so it wouldn't hurt to know the differences. One is called a trace fossil. Basically, a trace fossil, when I think of this, I think of when I watch CSI. You guys know those like detective-y type shows? And they're looking for evidence that somebody killed somebody else, right? And since no one witnessed the crime, hey, there's a hair left behind. You were there. That's kind of like trace evidence. Well, the way a trace fossil works is that there's evidence that something existed, like say a footprint, right? Or like a hole in the ground, like a burrow, right? If you find something like that, you didn't actually find the animal. You didn't even find the animal's dead remains. You know what I'm saying there? But you found evidence that an animal was there, right? So if I find a footprint in the dirt somewhere outside, hey, someone was here at some point, right? Maybe a silly story, but maybe this will stick with you. One time I was driving back from Calgary, went to a concert when I was in university, and we had to drive back from Calgary to Lethbridge, and horrible snowstorm happened. Like when we drove up to Calgary, roads are fine. We get back in the car after the concert, and it is a whiteout. But we had to get back. I had school the next day, right? And so I remember we were driving down Highway 2, and I was trying to figure out whether or not to turn off at Clarisholm. You guys know how you can like go east on Clarisholm way there, or go straight down. And what ended up happening was a car, and there was like no traffic on the road because it was horrible conditions. A car had just finished coming down that road towards me and turned off. And I decided to go that way. And you know the reason why? Is that I could see his tire tracks. And I knew that that car had made it to Clarisholm safely. Therefore, if I followed its tire tracks in the whiteout, I knew I was going to be safe because clearly it made it to me safely. Does that make sense? So therefore, I knew I wasn't going to go off the road because I had no idea where the road was anymore, right? And I just followed its tracks. Does that make sense? I know that's kind of a silly analogy there, but to me that's like a trace example where I could then follow the tracks of the car and know where it came from. In the same way, that would be these sorts of fossils. A different type of fossil then would be a cast fossil. And this would be like where a fossil has a mold and then the mold gets filled in. So you guys know how you make like jello maybe in some of those like funny little shapy containers there? And there's like a mold that takes place. Um, what ends up happening is these fossils right here, some other stuff gets filled in the spot. And so this is considered to be a positive image because you actually have like physically like the same object made. So you know how you take the jello out of the mold? That would be an example of a cast fossil. You know how I just used the word you took the jello out of the mold? Well, that's a mold fossil. A mold fossil would be when you have an impression left behind, but there's nothing there anymore. Because like the bones or the skull or whatever it was has eventually decayed, but it left behind an impression of itself. Um, Maybe another analogy would be you guys go to the dentist. Anyone ever have to like bite into the trays to do like the impression of your teeth? Okay. So when they refill those impressions to like make a model of your teeth, that would be the cast. But when you bite in to the thinger there, and then you take your teeth back out and there's like the gaps left behind, that would be this one. This is the one that's the gaps left behind, and this is the one where you've then filled in the gaps with something else. Okay. The final type of fossil we'll talk about a little bit later on in our course actually is a true form fossil, and that's where something gets buried so quickly and so efficiently that it's actually exactly preserved. And these are probably the most rare types because like it literally is still right there in pristine condition. These three things right here, you're talking about the thing being long dead and gone. But here, the bug is still sitting inside something. Does that make sense? Okay, so this slide right here then just talks about the four different time scale eras. And I don't know if you want to maybe write this down on a fresh page in your notes here. Here are the four eras that what we call. The oldest one is Precambrian. Then there's Paleozoic. Mesozoic is known as being the era of dinosaurs. And then the current one known as the Cenozoic era. Okay. And we'll talk about those more in detail on a future lesson. But I just want you guys to know the terminology of the four. Precambrian is oldest, then Paleozoic, Mesozoic, Cenozoic. We have another name for it, by the way. Sometimes you might hear them call it the Grand Record. A Grand Record would basically be like that first slide I showed you where there's the picture of like the timeline. Any sort of timeline would be a Grand Record. Okay, so I want to tell you about an old paleontologist. His name was James Hutton. And he had a theory that is really very integral to this whole concept of geology. It's called, oh, where is it here? I'm going to skip a slide if I can, okay? I'm going to come back to the one I missed. Hutton had an idea and he called it uniformitarianism. That is like the longest word I've ever seen. Uniformitarianism. Here's the definition like in people words. Well, actually, no, let me go back a slide here, actually. This is a picture right here of some earth that Hutton excavated. And it's not a great picture, but can you guys see how all of these layers right here are nice flat strata? And I just described to you guys to start our lesson that outcrops let us literally see all these layers one at a time. And then he came to something strange. He came to something where all the layers were going up and down. And he was like, well, this just ruins the entire idea of the laundry basket basically being layer by layer. But he had an idea. He said, okay, I was not around thousands of years ago or however long ago this was. But he had an idea. He said, well, we have earthquakes now. What if there were earthquakes thousands of years ago? Right? Now, was anybody alive thousands of years ago to record the earthquakes and make note of it? Well, no. But that's kind of the idea. The idea basically is that geological processes in action today have always occurred in the same way. Basically what it means is if we have earthquakes now, well, we must have had earthquakes thousands of years ago. If we have volcanoes now, we must have had volcanoes thousands of years ago. If birds breathe in oxygen now, we assume that birds breathed in oxygen thousands of years ago. We know that plants use carbon dioxide now. We don't have evidence to know for sure that they did, but is there any reason to believe that plants wouldn't have also used carbon dioxide millions of years ago? That's the idea of uniformitarianism. The only problem is it's not something you can prove, and that's the whole problem with this section here, right? Scientific evidence strongly suggests these things, but I can't actually go back in time. And so I really think this is an important concept here because we have to assume that what happens nowadays could have happened years and years ago. So here was his theory. His theory was that the reason why these layers are all sideways is that maybe there was a mudslide, or maybe there was an earthquake, and a large section of rock tipped over and fell. He said, well, that could happen today. Why couldn't that have happened 25,000 years ago, or 250 million years ago? And so that's actually where this slide right here comes from. I'll read off the notes here. In 1700s, James Hutton observed a rock strata, tried to get evidence of past events. It was supposed to be flat like this, and then he started seeing ones that were like this. And so he proposed that they originally were flat. He proposed that it always was like this. And what ended up happening is that, like, this section right here, snag those somehow. Well, okay, you guys, I think you guys get what I'm going for, right? That those sections right there kind of like tipped over and fell. It makes sense. So he was thinking, well, maybe there was an earthquake, or I haven't mentioned this one yet, but what about retreating ice sheets? We believe that Earth has been through multiple different ice ages as well. And so maybe as glaciers were formed and ice moved forward, maybe that caused these rocks to tip. And so that's kind of where this picture came from. Okay. The word that I need you guys to write down then is the idea of absolute age. So again, up till this point, we believe that, highest levels are youngest, oldest levels are at the bottom, but we still have no way of knowing the absolute age. We know the relative age, but we don't actually know for sure. Well, this one's 17 years old, this one's 42 years old. Right? So that's where the final part of my lesson is going to come in and talk about how they managed to figure out the idea behind how old things really happen to be. Does anybody have any questions so far, by the way? So let me go to this slide here now, and let's talk about the problem of absolute age. We know, to the best of our ability, we think we know relatively how old things are compared to each other, but it took until about 100 years ago, 150, maybe 200 years ago, somewhere in that time frame. You might have heard this name before. Her name was Madame Curie. She's famous because she discovered radiation poisoning. She didn't know it at the time, but she was working with radioactive materials, and she actually died due to radiation poisoning because she didn't actually know that she was poisoning herself. She was working with like curium and radium and all sorts of. Now we're very careful with these things. She had no clue, and so she poisoned herself by accident. So, anyways, another side story there. She discovered that certain elements were radioactive, and they emitted off invisible rays. Okay? And then eventually a guy named Ernest Rutherford, who's Canadian, by the way. Actually, no. He's New Zealand, but he worked in Canada. He actually taught in Canada for a while. He was actually able to figure out the intensity of radiation. And you guys might have seen some of these things before. This is called a Geiger counter. Anybody ever seen those or heard of those before? Basically, it's a machine that if something is radioactive, you would put the little sensor near it, and it's going to go beep, 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 right? It's kind of like like a metal detector, right? Only what it does is it detects how much radiation is being given off. And so this is like the radioactive symbol right here, and this is the little wand you'd use. What he discovered is that the radiation can be detected by how many particles were being emitted every second. So the more radiation there is, the more particles you're getting bombarded with. Okay. Now here's where this matters. Rutherford discovered that all radioactive materials had what was known as a consistent half-life. Okay, let me try to describe this first. He played around with the element called thorium, and he discovered that every 55.6 seconds, it was half as radioactive as before. So, like, it used to be this radioactive. 55 seconds later, it's half as much. 55 seconds later, it's half of that. 55 seconds later, it's half of that. He discovered it was very consistent, which was kind of cool, and it led to this graph right here. This one I've got sitting in the corner, where, like, see how there's the 50-second? Where's 50%? 50% is right here. See how it started at 80? Half of 80 would be 40. And so 40 happened after 2 seconds. What's half of 40? 20. 20 happened after 40 seconds. 4 seconds. What's half of 20? 10. 10 happened after 6 seconds. Half of 10 is 5. 5 happened after 8 seconds. And so every 2 seconds, it seems to be half as much. And that's kind of how radioactive materials work. Now here's where uniformitarianism comes in. We can test radioactive materials today. We assume then that however radioactive material properties works in the year 2018, that it existed in the exact same way 100 years ago, 1,000 years ago, 1,000,000 years ago. Does that make sense? Same problem though. We don't know for sure. We're pretty sure, but I like to say this in all of my sciences. Never say never. Like chemistry and physics have changed drastically. It wouldn't surprise me if we discover new information and we just tweak our theories. So here's the definition you guys need to know. A half-life is the amount of time it takes to have half of what you have. Let me give you a different real-world analogy here. Imagine that you have $100 and you want to start spending your money, and so you want to spend half your money. Ooh, that does not sound like a good cough. That sucks. Okay. What's half of $100? Okay, so let's say it takes you 10 minutes to spend $50. Well, then you want to spend half your money again. Well, half of 50 is now 25. That's also 10 minutes. And then half of 25 is 12 and a half. That's another same amount of time, right? And so it seemed to be very, very consistent. This was actually useful then in trying to date and age different rocks. Okay. What I need to talk to you guys about is something called carbon-14. Okay. So brief aside from the geology, do you guys remember what the 14 stands for in carbon? It means this. It's carbon-14, and then carbon has 6 protons. What does it mean for this particular carbon? How many neutrons does it have? Yeah, that's what it means. This carbon has 6 protons, and then it needs to have 8 neutrons. And it's a very unique variety of carbon because not many carbons have 8 neutrons. Some do, some don't. And what's unique about carbon-14 is that it eventually turns into nitrogen-14. Okay. Now, nitrogen-14 will be an N with a 14 and a 7. What does it have? Well, it has 7 protons and 7 neutrons. Basically, what seems to happen is one of your neutrons goes down and one of your protons goes up. And that's actually possible. It's called nuclear chemistry. We don't cover that in this course, but if you eventually get to a certain part, that's actually how nuclear reactions take place. You can actually change protons and neutrons and electrons into each other in extreme cases. And so slowly over time, carbon-14 turns into nitrogen-14. Okay. Now the words I need you guys to know are called parent isotopes and daughter isotopes. And they honestly make exact sense like you'd imagine. What you start with is a parent, and what you end up with is called a daughter. So using the words that we've got right here, who's the parent isotope? Carbon or nitrogen? Good. And then the daughter is the nitrogen. Okay. So slowly over time, carbon-14 turns into nitrogen-14. And we can actually measure it. It takes 5,730 years to take half of carbon-14 and turn it into nitrogen-14. That's pretty much most of Earth's human recorded history. This is where uniformitarianism is the linchpin to this. If carbon has always turned into nitrogen at this rate, then the math should work out. But if the rate somehow has changed over time, then the whole thing falls apart. Okay? But if that's true, then what we can do is we can say as soon as an animal dies, it can't ingest any more carbon. Okay? Yeah, boy, that cough sounds horrible there. Okay, so here's how this works. When you or any animal dies, you cannot take in any more carbon. Okay? Your body will then start to decay. And your body is made of different carbon amounts. Okay? And some of those carbons are carbon-14s. Slowly but surely, they will turn into nitrogen-14s. And your body will decompose. And I mean, that's why we bury bodies, right? Because eventually, the remains will like return back into nutrients in the soil and start the whole process of life over again, right? Circle of life, Simba, Lion King, that kind of concept, right? So, yeah. Okay. Here's the idea then. By measuring the amount of carbon-14 remaining, scientists could figure out how old the fossil is. Here's the problem, though. The daughter nucleus, though, is nitrogen. And nitrogen will escape because it's a gas. And so literally what happens, I got a picture here, is that this is what something looks like when it dies. And slowly over time, it decays. The carbon-14 turns into nitrogen-14. And it looks like this, and this, and this. Now, if it decays into something else that's solid, it basically just turns into a new solid material. But since this stuff decays into nitrogen gas, the gas will escape, and then slowly over time, the bones are completely, I don't know, gone. Does that make sense? So it's kind of challenging to figure this out because there's actually not anything left to look at. Okay? So we have to make an assumption, and that's that same uniformitarianism. We assume that the amount of carbon-14 that goes into organisms has always been the same. So if we assume that 1 out of every 1,000 carbons is carbon 14 today, then hopefully a million years ago, 1 out of every 1,000 carbons was also carbon 14. That's the assumption. We can't actually check it though, right? So here's how the math works. This is literally the one application we have in this unit. And so if you guys can, I'm going to go to the very, very last example, and I'm going to try to show you how they determine how old stuff is. This is basically the concept. I'm not going to use carbon and nitrogen examples, though. I'm going to use other half-life examples. So the first one here is we're going to take some uranium-238, and we're going to turn it into lead-206. Okay. Who is the daughter? Yeah, told you. This is the daughter because the parent turns into the daughter. Okay. So you used to be made out of uranium, and slowly over time, the uranium is turning into lead. Will you still have some uranium left, though? Yep. Right. Just like as the dead groundhog dies over time, will there still be, some like not quite decomposed bones? Yeah. Right. It takes a long time for it finally to be completely gone. Right. But you'll still have something left. So what I'm going to tell you is that 30% of the sample is lead-206. What that means is that there's now 30% daughter nucleus. What percentage of uranium would there be then? If 30% of it's now the daughter, how much of it is the parent? Good, 70. Is everybody okay with that? So what I'm going to now say is that based on this information, we have 70% left. Have we hit a half-life? Has it been cut in half yet? Not yet. Okay. So what we have to do is we have to use a table in your textbook. If you guys have your textbooks nearby, can you turn to page 577 or go find someone who has one nearby? Or, is it on this tab sheet here? No, it's not. Shoot. Maybe I can get it up on the screen too, actually. Bear with me for a second here. Oh, you know what I can do? I can use the picture that was in our notes. I take it back because I have one of those in our notes here. What you're looking for is a graph that looks something like this. There's like a graph of it. It was on, what was it, 577? 577. Didn't you go get your book? Or find someone who has one nearby. 577. Nope, that's clearly the wrong page. What page is it on? Maybe it's 557. Sorry, I screwed up. It's 557. Sorry, guys. That's the wrong page. 557. 2517. Rylan, I'm going to steal yours briefly just so everyone can see it. What we're looking for is this graph right here. You guys find that one there? 557. Okay. That graph should hopefully look something like this. I'll just draw a basic one out. It goes like this, and then it's kind of slowly decreasing. Okay. How much parent nucleus was left? You guys remember the number we had? Okay, and I believe the way this graph works is that along this axis right here, it goes like 100, 90, 80, blah, 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 all the way down to 0. So you guys need to find where 70 is, find that marker, and then look right here and try to figure out how many half-lives it's been. So as you go down, 70 is right about here. As I go down, you guys want to just maybe gather around one textbook here, maybe? Can we all just meet in one spot? Here, where's the central location? Try to come right around here. I'll try to show you how this looks here. Just gather in here. I wish I had it up on the screen. I'm sorry, I wasn't smart enough to think of that. Can you guys see how the 70 is right here? So what you would do is you'd take this marker right here, and to me it looks like it's about after the first second, about 2.5 down here. So 2.5 would be about right about there. Is where like this 70 leads to. It's not even to one half-life, which doesn't that make sense though, because 70% is not even half yet, right? So how many half-lives is it? That would be 0.2, 0.4, 0.6, 0.8. So I might say it's about half of a half-life. Make sense? So Whereas like if I give you a different number like 40, you'd take 40, you'd go over to here, and you'd figure out how many half-lives you have. Okay. Once you figure out how many half-lives you have, all you got to do is this. I need to go back to the slide. You guys can just watch from here. If we agree that based on this graph right here, 70% right here led to about like a half of a half-life, well, it says that uranium takes this long to get cut in half. But we don't even have a full half-life. We have half a half-life. You know, all you have to do then is take this number right here and times it by half. Because a full half-life would take this long. But did it even get cut in half yet? No. Half of it got cut in half. So all you got to do is take this number and times it by half. So 4.47 times 10 to the 9 times by a half would be how old we think the rocks have to be. And that's basically, you guys can sit back down, I guess, if you want. That's basically how scientists believe they figured out how old these rocks are. They find out how much fossil is left, and they times it by its half-life. So if there's 3% left, 3% is probably like 7 half-lives. Can I say this a few times here? 50% would be 1 half-life. Does that make sense? What would 25% be? 2 half-lives. What would 12.5% be? 3 half-lives. And so if I told you that, like, of all of these bones that were left here, let's say that I told you that there was like 5% left. How many half-lives would it take to get to 5%? Well, 1 half-life would get you to 50. 2 half-lives would get you to 25. 3 half-lives would get you to 12.5. 4 half-lives get you to about 6%. 5 half-lives would get you to about 3%. I wanted 5%, so you're talking about 4.5 half-lives, give or take. All you got to do then is know how long a half-life is, and times by 4.5. So in our example here, since it was only half of a half-life, because we didn't even cut it in half yet, we just do half of this number. Does that make sense? If you guys wouldn't mind, why don't we do the question on this on your assignment? Because I'm done my notes for the day now, actually. Why don't we do the question number 6 together as a group, and then we can call it a day. This is literally the only application thing I have in the entire section, is the idea of how do we figure out how old things are. So this is question number 6. It says that a fossil has 20% potassium-40. We need a little more information to solve this, though. So you need to go to that page that I was just on in your book, and there's a little chart in there. And so I'm sorry I don't have this in front of you. You guys need to have your books or borrow someone's. Can you guys see that potassium-40, if you have your book with you, is what you start with? The potassium-40 turns into argon-40. Okay, it's on that same page 557. There's a little chart up there. It'll say that potassium-40 turns into argon-40. I'll give that one back to you. So let me just write this out here. According to chart says that potassium-40 turns into argon-40. Okay. So who's the daughter, who's the parent? Yeah, argon's the daughter, potassium's the parent. Okay. And you have 20% of this left. Has it been cut in half once? Yeah. Has it been cut in half twice? What would 2 cut in halves get you down to? Yeah, because half would be 50. Half of 50 would be 25. We're down to 20. Has it been 3 full half-lives yet? Not quite 3. Close, but not quite 3. Which means you must have 80% daughter. So slowly over time, this has decayed from this guy to this guy. The only things we need to then figure out, we need 2 numbers. One, we need to know how many half-lives it's been. So the number of half-lives it's been. And we're going to multiply that by how long a half-life is. So the first one's really easy to do. If I want to figure out how long the half-life is, it literally will tell me in that chart. So if any of you guys do have your textbooks next to you, how long does it take potassium to turn into argon? Can you read that for me, Caleb? 2.2, but then probably times 10 to something, right? Can't just be 2.2, right? Oh no, it's 1.26 times 10 to the 9. Do you see that? That's the third column there. 1.26 times 10 to the 9. So out of the chart, it's 1.26 times 10 to the 9 years. That's how long it takes for half of your potassium to turn into argon. Did half of it change? Well, more than half. So the next thing we got to figure out is, well, how many half-lives is there? So the next thing you want to do is go to your chart, that little like graph there, and you want to figure out where 20% is, and you want to kind of trace the graph over and down and figure out about how many it happens to be at 20%. I know that it's more than 2, because 2 half-lives is 20%, but it's not quite 3. So you got to kind of try to estimate it and say, like, is it 2.1, 2.2, 2.3? So I'll borrow your book if I can here. And then I can do this with you guys one at a time if you want. So I'll do it with you guys here. 20%'s right there, right? So if I follow the 20% over to there, and then down to about there, it's after 2, right? But not 3. I feel like it's 2 point, okay, this is going up by 0.2s, so that'd be 2, 2.2, 2.4, 2.6, 2.8, 3.0. So I feel like this would be 2.4 more or less. So I can do that with you guys each individually if you want later, but according to what I figured out there, I think it takes about 2.4 half-lives. So 2.4 half-lives, this is how long a half-life is. All we have to do is times those numbers by each other. And now we think we know how old that rock is. So I'll just grab a calculator and times it real quick. 2.4 times 1.26 times 10 to the power of 9 gives me this number here. 302400000 years. And that's where the theory of deep time came from. Before the idea of being able to do radioactive dating, scientists actually had no idea how old the Earth was. Now, I got to point out a couple of things. First of all, I'm not actually trying to say that I don't believe this is true, but it very much depends on the fact that if radioactive materials have decayed at this rate, they've always decayed at this rate, right? That whole idea of uniformitarianism. If it's always taken 1.26 times 10 to the 9 years for potassium to turn into argon, then sure, this holds true. But if that number has ever changed over time, well, then the whole math thing just gets blown out of proportion, right? So, but working backwards, now we can give an age to rocks, right? And so if we can age this rock right here, and we know this one is older than it, and this one is older than it, then we can start to get some general time frames for how old the Earth is, which is why there's the thought that the Earth is like 4.5 billion years old. Does that make sense? Okay. When I do the last one with you, the other 6B question, I'll do it with you because I don't mind helping out here. So what was 6B? 6B says a moon rock contains 6% of a daughter nucleus. And the daughter nucleus is strontium 87. Okay. So what this means is that we've turned into strontium 87. Use your textbook if you have one nearby and tell me what turns into strontium 87. So look in that little chart. What turns into strontium? Rubidium? What number is after rubidium, by the way? Rubidium 87? Okay. So it looks like rubidium 87 turns into strontium 87, according to that table. And we have 6% strontium. How much rubidium do you have left then? Because don't these two numbers have to add up to 100%? Okay, bear with me. I'm going to finish and then we'll go here. Has this thing been cut in half yet? Not even close. So the first thing you got to do is go to that little decaying chart thing here and find where 94% is and figure out how many half-lives it's been. And it's not even going to be a full half-life. Right. So I'm going to borrow yours again here, Ellen. Try this again. I'll show you guys one more time. And again, I'll do this with you guys individually if you want. 94 would be right about there, I'd say. There's 92, 94. And if I drop this down all the way there, it's like halfway in between that box. If these boxes are going up by 0.2s, because that's 0.2, 0.4, 0.6, 0.8, and 1, I think halfway between that is 0.1. So based on me looking at that table there, I believe that this has been 0.1 of a half-life. The only thing I have left to do then is times by however long it takes for half of this to change. So help me out here. What was the time associated with rubidium to strontium? 10 to the power of what? 10. Okay. So all I would have to do is times these two numbers together, and that is how many years it would be. I'll let you guys do that part because I've done almost everything else for you. So let me do a quick summary here in the 1 minute I have before you got to go. What we talked about are probably three main concepts. The first one is relative dating. The idea that old stuff's at the bottom, young stuff on top. Problem with relative dating, other than the fact that you shouldn't take your sister to prom, sorry, bad joke, is that we don't know exactly how old things are. That's a problem. But with carbon dating and radioactive dating, there is a way to calculate this. But there's still one more problem. It's not a problem so much as an assumption. We assume uniformitarianism, that what we recognize as happening today, we assume that it's happened that way through all of Earth's history. We don't have any reason to believe it doesn't, by the way. But we do have to make that assumption because we can't actually go back in time and make sure that the half-life was actually the same thing 10,000 years ago. Okay? If that's true, though, that's what leads to the idea of deep time, being that we think that Earth is billions and billions of years old. So, does that make sense? Cool. Okay, I'm done. Thank you so much, guys, for being patient with a really long lesson. So we'll do the next topic tomorrow.